Hello everyone. Good morning, good afternoon, and good evening to all of you. Myself, Sumeet Pawnikar. I'm part of a Intel organization, and I'm working on the thermal management, power management, and performance optimization on Intel SoC-based Chrome systems. And today I am here with Tim from Google to present and give a talk on thermal management on Intel-based systems in coreboot. So here is the table of contents. We will briefly touch upon the couple of points here, like introduction of the Intel thermal management in coreboot, traditional thermal solution DPTF, also known as DTT. There are a couple of core changes for the common structure for DPTF, and the last and important point is there is a new runtime DPTF policy generation introduced recently. So why do we need a thermal management? In today's computing world, there are varieties of systems and devices out there in the market, like client, edge systems, IoT devices, servers. All these systems require the reliable and efficient thermal management solution. Basically, first, for the thermal management, it is must to have a balance between power and performance in terms of the best performance with the higher speed, also to improve the battery life and save the energy. And the important point is how we can optimize the power consumption for the different active workload scenarios. So what is the Intel's solution for thermal management? So it is known as a DPTF, Dynamic Platform Thermal Framework. It is also known as DTT. This is recently added new name for the DPTF. There are two types of majorly the thermal components on the system. One are the heat generators and other are cooling devices. So from the DPTF software point of view, these thermal components referred as participants. There are different participants like CPU, fan, TSRs, which are like onboard thermal sensor registers, and the battery charger. Under DPTF thermal solution, there are different types of cooling policies present. Majorly, these cooling policies are divided into three different policies, like active policy, which is based on the fan cooling, passive policy, which is majorly focused on controlling the power on the system in terms of controlling the voltage and frequency. And the last and the important one is the critical policy, to prevent the system from getting damaged whenever the system or any thermal participant hits the critical temperature. This critical policy initiates the system-wide graceful shutdown to prevent any system getting damaged. There is a battery charge rate control policy, part of the passive policy, which helps to control the battery temperature and the charging circuitry temperature. Now, this DPTF thermal management solution is implemented with the ACPI methods implementation, which interacts with the low-level embedded controller EC framework, also coreboot firmware, and with the Linux kernel driver. These ACPI methods are populated to the user space applications. Here, DPTF is the user space application, which helps to control the temperature and cool down the overall system temperature. This is the next slide, which talks about how this DPTF thermal management solution from the Intel is implemented inside the coreboot. Here, majorly the DPTF thermal management solution are distributed in terms of the code layout for four specific sections. One is the Intel SoC specific implementation. Another is the Intel reference board implementation. Third one is the Google reference board implementation. And the last one and the important one is the customer design board specific DPTF code. Here, bottom of the slide, you can see there are reference static ASL files. These ASL files are like charger.asl, cpu.asl, dptf.asl, fan.asl, and thermal.asl. Please note here, these ASL static files are under the directory coreboot source SoC Intel common ACPI DPTF. So this is the common ACPI DPTF ASL files. Moving to the next slides. Here on this slide, you can see that implementation of the Intel SoC specific thermal management solution in terms of the different ASL files, which are under coreboot source SoC Intel directory. Left hand side, you can see there are a dozen of Intel SoCs directories present. Important is the common directory. Right hand side, you can see there are different types of ASL files: thermal.asl, cpu.asl, dptf.asl, charger.asl, and fan.asl. Initially, when we started implementing the DPTF for the thermal management solution, we had implemented that in the thermal.asl file, and which was part of the Braswell directory, and under Braswell ACPI DPTF thermal.asl file was implemented. After implementing in the Braswell directory from a Braswell generation to the next generation, it seems like the ASL files used to being copied from a previous generation to the new generation, and it looks like all the code is just a copy paste. So that's why you can see there are Braswell, Baytrail, Skylake directories has thermal.asl file, and similarly for the other ASL files as well. What common code infrastructure brings here, that under the common we have moved all this ASL file implementation, and there is no need to duplicate the ASL files anymore for the new Intel SoC specific implementations. Now going through each of the ASL files, this thermal.asl files has the definition and the implementation for the participant for thermal management. cpu.asl file, which contains the processor throttling control and processor performance control knobs in terms of the ACPI methods. Charger.asl file, which contains the battery charger rate control and also the battery and the charger information. dptf.asl file contains the policy information, and it also populates the active, passive, and critical policy to the above layer. Last one is the fan.asl. Fan.asl contains the fan specific controls and the fan state on or off, speed level control in these fan.asl files. So these are the major DPTF specific ASL file implementation in these directories. Note that this is the generic ACPI based method implementation to have the common thermal management solution under coreboot. Moving to the next slide. So this slide talks about the Intel reference board implementation for the DPTF. So the directory structure is coreboot source mainboard Intel. Under that left-hand side, you can see a couple of directories which are having the different reference boards from the Intel, and all these reference board designs have the thermal.asl and dptf.asl files. Majorly dptf.asl file under this Intel main board contains the board specific details and the sensor specific information, and the dptf.asl file under this main board directory contains the Intel reference board sensor information and what type of the policies are present and how to control those different policies with the different participants. So moving to the next slide. This is the slide which talks about how the different customer boards implementation for the thermal management inside coreboot. So under the directory coreboot source mainboard Google hatch variants. Here hatch is one of the customer board reference which is majorly provided from the Google as a reference board, and under variants you can see there are many variants of the hatch board. Left hand side you can see more than around 20 reference customer boards are there for the hatch variant, and right hand side you can see the dptf.asl files which contains the every variant specific dptf implementation. This dptf.asl file contains the specific control knobs in terms of the temperature and power limit controls, also the fan speed control, and last one is the how the battery input charge rate is being controlled. So these different files are for the different various boards or the system from the customers, and these are the independent from each other.
With this slide onwards, I would like to request Tim from Google to explain next slides. Thank you.
Hi, my name is Tim. I'm an application processor firmware engineer at Google. I work on Chromebooks. I'm on the platform enablement team. So my job is to bring up Chrome OS and its firmware on new platforms. As Sumeet mentioned, thermal management is an incredibly important part of keeping these laptops both power efficient and powerful enough for people to use every day. But what I recognized here is that we have a problem with these static ASL files. It's tricky for people who are not experienced with ACPI or BIOS in general to deal with these ASL files. ASL is ACPI source language. It's a language that's kind of like C in a way, but in the end it's interpreted and the kernel runs this bytecode that executes these methods. So these ASL files are a little bit hard to use. So what I decided to do was add a new driver to coreboot that would generate these policy tables at runtime. And so I'm going to talk a little bit about this. I'm going to talk about where these files live, or excuse me, where these tables live, SSDT versus the DSDT, the code flow of this new driver. I'm going to show a little example of what some of these entries look like, and we're going to talk a little bit about all that. So again, as I said, it's kind of difficult for non-ACPI experts to understand and modify these ASL files. But we have this nice configuration language in coreboot called device tree, and this is the typical way that we will configure device-specific things to control, for example, ACPI tables. These new policy tables are generated at runtime instead of coming directly from static files. There's two main ACPI tables that we're talking about here. As I mentioned, there's the DSDT, which is the differentiated system descriptor table, And there's the SSDT, which is the secondary system descriptor table. The ASL files all ended up in the DSDT. These new policy tables end up in the SSDT. And that's fine in this case. The only difference really between the two is that the DSDT cannot refer to devices that are defined in the SSDT. But in this case, all the data is generated at runtime, so all the devices live in the SSDT, and we don't have a problem sharing code between the two tables. Next, we're going to talk a little bit about the flow of this data. So before, it was just an ASL file that got included in the DSDT, which was just copied into memory and given to the kernel. This is a little bit more complicated behind the scenes, but the end user doesn't have to worry about this. Basically, we have a tool in coreboot called sconfig, which is a code generation tool. It takes in our device tree and generates .c and .h files at build time, which basically consist of arrays of structs containing all the data from the device tree. During RAM stage, when memory is up, we'll call into all these device drivers to emit AML, which is ACPI machine language, into the SSDT. The DPTF driver will call into the ACPI gen library to emit the AML bytecode. All this data is then passed to the OS via the coreboot tables. The operating system will parse these DPTF tables and leave entries in the sysfs. And the DPTF user space application will come along and consume these sysfs entries and perform the necessary thermal management. This is just a small example of what it looks like in the device tree. We've got the DPTF device itself, which is a PCI device on most Intel SoCs. We're saying here that we've got a chip, which is the way we configure information for a device. This is an example of what a passive policy looks like. As you can see, this is pretty easy to read here. We've got one passive policy that what it's going to do is pull the temperature sensor 0 every 5 seconds and check if it has reached 90 degrees C. If it has reached 90 degrees C, then it's going to start to throttle the CPU. And so it's going to look into the CPU's performance states table to look at the different states it's able to put the CPU in to lower its power consumption and hopefully reduce the temperature seen on that temperature sensor. So there's several advantages to using this runtime generation of the policy tables. We get to remove a lot of duplicate files and code. As I mentioned before, it's much easier to manage for non-ACPI experts. If you're going to be using coreboot, you're probably going to be familiar with the device tree anyway, so this makes it easier. From my point of view, I'm working with OEMs and ODMs to bring up new platforms, so I want this configuration to be simple. Forcing the use of ASL doesn't help this at all. It makes things more complicated, and it's harder for like the power and performance teams on my side to go back later and tune these and see what the values actually are, because the tables are kind of hard to read when they're in ASL. And this also gives us another advantage in that it's also simpler to support a new SoC. The driver tries to abstract away as much SoC-specific data as possible, which means we don't need to keep around these ASL files for each SoC either. And if you'd like to see some implementations of what this looks like, we've got here's a couple examples you can look at. Intel's Tiger Lake reference board, their RVP. You can find an example of a complete device tree there. And device tree also allows the concept of like a base tree and an override tree. So a base board can provide a default implementation, and a variant board can override specific parts of the policy if desired. So we could say all boards in this reference platform have 4 temperature sensors, for example, and so it could specify all those and then maybe each board would only have different thresholds for each sensor. And so they could just set that up instead of having to say that all these sensors exist and the thresholds as well. So if you'd like to see some examples, you can Google Voltaire reference board is a good place to look, because that one is actively being developed right now. And if you look in the variants folder under that main board, you can find things like voxel and Terador, and you can see their override trees and their DPTF parameters as well. And that's about all I had. Here's where we probably stop for questions.